From a group of 10 people, you randomly select 5 of them. What is the probability that they are the 5 oldest people in the group? All right, so let's try to see if we can use a counting rule to answer this problem. With counting rules, the strategy starts with being organized. Determine N, how many items are available to select from. If you have difficulty visualizing that, you can list them out and count them. Also determine R, the number of trials we will perform. In other words, how many spaces do we need to fill? Or if you're having trouble determining that, think about the process and ask yourself, what would be one trial? And then count how many of those you're going to do. 3, determine if the trials are dependent or independent. If they are dependent, it means that we are doing selections without replacement. If they're independent, then we are allowing repetitions. So let's begin by getting organized. First of all, how many items do we have to choose from? N equals 10, because there are 10 people from a group from 10, right, that we're going to choose from. 10 people. R, how many are we going to be selecting out of the 10? Or in other words, how many spaces do we need to fill? It says randomly select 5. Right, so we have 5 spaces to fill, or 5 positions in the group. And finally, are these dependent or independent trials? In other words, if it's dependent, that would mean we're doing it without replacement. Or another way of saying this is that repetitions are not allowed. Okay, so let's visualize this. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. And we have 1, 2, 3, 4, 5 seats to fill. We want to know the probability of selecting the 5 oldest, so let's highlight 5 of these to represent the oldest ones. All right, so let's say we choose this person to the first spot. Can we choose that person again? Well, no, we can't, because we need to have all of these spaces filled with 5 different people, and so we can't use the same person twice. Right, so then we know that repetitions are not allowed. Okay, now that we've figured that out, the next question you want to ask yourself is if order matters. Does order matter? The reason that we want to always ask this is because there's one formula that we might be able to use, the combinations formula, NCR. And if we can use it, then our search is over. And if we cannot use it, then at least we've crossed one option off of our list of possibilities. And combinations is the only one in which order does not matter. So it's a really good first question to ask after you've become organized with the basics here, right? So does order matter, right? So will it matter if I put this person here? If I select that person for the first seat or the second seat, does it make a difference? Well, the problem says that we want to randomly select 5. It doesn't say anything about arranging them in any kind of order. It doesn't say anything about different positions. It's not like we have a board of, like an executive board, say with a president, a VP, a treasurer, secretary, etc. We don't have any different ranks here. So it really doesn't matter the order that I assign them in. So we're going to say that order does not matter. Okay, so now that order does not matter, we can use the combinations formula. Now keep in mind, since order does not matter, I know I want to use the combinations formula, but also you have to keep in mind that if you don't ask these questions in this order, you might miss something. In other words, if you went straight to asking the question if order matters, then probably if you say no, it's going to be the combinations formula. But you also need that repetitions are not allowed. So without replacement, we need that as well. Okay, so that means we can use the combinations formula. The combinations formula is NCR, n factorial, over n minus r factorial, r factorial. Remember, factorial means that you multiply all the way down to 1. So let's put in our numbers here. We have 10 and 5. So filling in, we have 10 factorial. Then n minus r would be 10 minus 5 is 5 factorial. And then r factorial is 5 factorial. Now we can reduce this by expanding the top only as far as the largest factorial in the bottom so that we can cancel it off. All right, so notice that I have 10 factorial up here and 5 factorial is the largest factorial in the bottom. So I can do 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then expand 5 times 4 times 3 times 2 times 1, and also expand the other 5 factorial, 5 times 4 times 3 times 2 times 1. And what's going to happen is this 5 is going to cancel off, this 4 is going to cancel off, the 3 is going to cancel off the 2, and the 1. And we could have gotten that done a lot more efficiently by using a little trick. So we could have said, let's do 10 factorial, but only as far as leaving it right here. Instead of listing out the rest of the 5 factorial, we're just going to leave it as 5 exclamation point. And then in the bottom, we had a 5 factorial and another 5 factorial. So then this cancels off. And now we can simplify the bottom by expanding it 5 times 4 times 3 times 2 times 1. And you can either just, calculate each one of these as they are and divide them, or you can do some reducing to simplify. So I see that this 5 can cancel off with the 10 to become 2. This 4 and this 2 can cancel off the 8. The 3 goes into 9 3 times. And so I've got rid of everything in my denominator. I've already written down the 2 and the 3, and then I still have a 7 and a 6 left over 1. So what does that equal? 2 times 3 is 6. 6 times 6 is 36. So I'm going to do 36 times 7 and get 252. So that is the number of possible groups of 5 I could get, and only one of them is going to have all 5 of the members being the oldest. So I'm going to say that the answer is one group that's favorable out of 252 possible groups. Another way I could have looked at this is just using the multiplication rule for probability. Since there are multiple trials, and I can think of this as, let's say we use green to represent the oldest members. So I could have phrased that as find the probability of one of the oldest people, and then the oldest, and then the oldest, and then one of the oldest, and so on. So I would be multiplying these probabilities, but since I'm doing it without replacement, I have to consider what happened on each previous selection. Okay, and this looks very complicated when you write it all out like this, but all it really means is on the first selection, I have 5 of the oldest people out of 10 possible people. And then since I didn't put that first person back, I have now 4 out of a total of 9, and then 3 out of 8, and then 2 out of 7, and then 1 out of 6. And so what we're going to find out is that this reduces down to 2 times 3 times 7 times 6, just like we have there. So notice that this becomes 1/2. This could be 1/2. This could be 1/3. This can be 1/3. And then I have 1/7. So notice that I get 1 across the top, and then in the bottom, I get I have 1 extra, 1/2, 1/2, 1/3, 1/3, 1/7. Oh, that's because one of my 3's was combined with one of my 2's. So there's 6 there. So then I have 2 times 3 times 6 times 7, 1 out of 252. Okay, so that is another way you could have approached it. But notice how much more straightforward it is to use the combinations formula if we are successful in thinking through the conditions to make sure we can use the combinations formula. Mathematically, there's some calculations to be done there, but what else is cool is I have the combinations formula in Excel that I can use. So using the Excel formula, it's the word combine without the E on the end. Then you put in the number of possible items and then comma the number of selections, and you get the answer 252.